Hello, everyone. My name is Mike Borzak. I'm an Assistant Vice President and Senior Engineering Manager with WSP USA, and I am honored to be able to present to you today my topic, the Gerald Desmond Bridge Replacement Project, California's first vehicular cable-stayed bridge. So before I get started, I want to introduce you to some of the key stakeholders on the project. So on the first slide here, the left side of the screen, starting from the bottom, WSP is the program and construction manager. My role on this project was as the design review manager. SFI was the design builder. It was a joint venture consisting of Shimmick Construction, FCC, and Impergilio. Caltrans performed independent quality assurance reviews for the project. The owner was the Port of Long Beach, and the two funding entities, LA Metro and the Federal Highway Administration. So here's my outline, what I'll be talking to you today about. We're going to start out with some project overview and features of the new structure. Then we're going to get into some key design criteria and then move into some of the construction photos. We'll show the main span towers and superstructure, and then finish up with lessons learned and some Q&A. So project overview and features of the new structure. Just to get everyone oriented, the Port of Long Beach is in the southwest corner of the city of Long Beach. This purple line represents the limits of the project. It cut a 200-foot wide swath, really right down the middle of the port facilities. So there was a lot of existing infrastructure that this project had to get built around. It ties into the southern terminus of the 710 freeway on the eastern end, and on the western end, it tied into State Route 47. The project consisted of approximately 8,800 feet of bridge, which includes the approach structures, and the main span was a cable-stayed bridge which spanned the back channel, 2,000 feet long. Here's just a strip map, which provides a blow-up of the general plan and elevation of the site. Here's what the existing Gerald Desmond Bridge looks like. And here is the replacement structure. So I mentioned the Port of Long Beach is the second busiest U.S. port in the country. It's critical to not only the local area where it supports over 30,000 jobs, but also for the national economy. And the reason why is that approximately 15% of all containerized freight cross the existing bridge. Unfortunately, the existing bridge is functionally obsolete. There are 3 lanes going up the bridge. Once you get to the top, that transitions down to 2 lanes. As you can imagine, with a lot of truck traffic on the bridge, this leads to some heavy congestion and a lot of traffic tie-ups. In addition, the Port of Long Beach is big ship ready, and one of the drivers to replace the existing bridge is that these big ships can access the port facilities north of the existing structure because of the clearance envelope. And in order to compete with some of the other ports throughout the country, for example, on the East Coast, the Bayonne Bridge was raised in order for the big ships to access the ports of New York and New Jersey. So the Port of Long Beach is trying to compete with those other ports. So it was decided that replacing the existing bridge would be the way to go. So here's some design features about the existing and the new Gerald Desmond Bridge. So the bridge type you saw, the existing is a steel through truss. The new bridge is cable stayed. Out to out width, you can see the new bridge is quite a bit wider, over 156 feet wide compared to 70. The new bridge has 3 lanes in each direction, whereas the existing only 2. New bridge also has 10-foot shoulders, which can also serve as emergency lanes. And there's that vertical clearance. Goes from 155 feet up to 205, which allows those big ships that were shown on the previous slide to access the port's facilities. The grade is a little flatter. I know 6% versus 5% may not seem like a lot, but with a lot of truck traffic on this bridge, it does make a big difference. There is a 12-foot wide bike path on the new structure, so that's a good thing. And architectural lighting. There is LED lighting on the new bridge, and currently the existing bridge did not have any lighting. Here's just a schematic that shows that vertical clearance envelope, the increase of 50 feet from 155 up to 205 to allow those big ships to access the facilities. And here's an RFC drawing released for construction plans of the new bridge. So you can see it's a 2,000-foot long cable stayed structure. The main span is 1,000 feet, and it has two back spans that are each 500 feet long, and the towers top out at 515 feet. Here's a cross section of the main span. There's over 156 feet out to out. It's supported by edge girders on each end. These are 6 foot deep. You can see that there's a variable depth floor beam. It's around 10 feet at mid-span, and it tapers down to 6 feet at the ends. There's our 3 lanes in each direction with the 10-foot shoulders. So some of the unique elements of the structure and the construction methods. So there are a lot of firsts on this bridge. It's one of the first design build projects in the state of California. Back in 2010, the legislature allowed for projects to be delivered using the design build delivery system. Gerald Desmond was one of the 10 demonstration projects. It's also the first vehicular cable stay bridge in California. Those towers at 515 feet are the second tallest of any cable stay bridge in the US, has the highest roadway deck at 205 feet of any cable stay bridge in the country. It's also the first use of a modular swivel joint with fuses, and we'll talk about that later in the presentation. Also during construction, it had the tallest tower cranes used on any infrastructure project in the US at 515 feet, or excuse me, 585 feet. And it was the first use of pile tip grouting in California, and we'll also talk about that later in the presentation. Program delivery timeline, as you can see, the project's been around for quite a while. Conceptual studies started all the way back in 2002, and the bridge was just recently opened to traffic on October 5th of 2020. So now let's talk about some of the key design criteria on the project. So the items listed here, I'm going to briefly touch on concrete, steel, and thermal, and then do a bit more of a deeper dive on wind, seismic, and the accident and terrorist vulnerability assessment. So let's start with concrete. Concrete strength varies throughout the project. The main span reinforcing in the deck panels consisted of stainless steel. We had polyester concrete overlay, which was 1 inch on the approaches and then 1.5 inches on the main span. This table shows the various locations of the concrete pours throughout the project, the concrete types, and then you could see the strengths varied from 5 KSI all the way up to 7 KSI. The steel design criteria, all structural steel except the plates were grade 50. Plate steel was grade high performance steel 50W, except for the ATVA plates. And we'll talk about that later on, where they bumped up the grade of steel to 100W. Thermal criteria, you can see the steel and concrete temperature ranges. I also want to point out that there was a significant number of mass concrete pours on this project. These were elements that were greater than 7 feet thick. Cooling tubes were used to make sure the temperature of the concrete didn't get too hot. Those pours were made for all the pile caps, solid columns, bed caps, and abutments. So now let's talk about wind analysis. So cable stay bridges are inherently flexible. It's really built into their DNA. However, because of that flexibility, they're susceptible in high winds to excessive vibrations. And in order to ensure the stability and safety of the structure has to be tested in the wind tunnel. So 2 wind tunnel tests were performed. One was on a short length of section. This is a sectional model. And then a narrow elastic model wind tunnel test was performed. These were conducted at the Research Center for Wind Engineering at Southwest Jiaotong University, which is in China. This contains the world's largest boundary layer wind tunnel. So there were 3 aerodynamic study phases that were performed. Phase 1 had 3 components. It had a wind climate analysis, a sectional model wind tunnel test, and then a wind buffeting analysis. Then we moved into phase 2, which consisted of an aeroelastic model wind tunnel test. And then finally, phase 3 was a stay cable, rain, wind induced vibration, and pedestrian comfort study. So let's look at phase 1. They used climate data from LAX and Long Beach airports. And with that data, they performed the first round of testing on that short sectional model. This was a 1:45 scale model of the bridge. The stability was checked in 3 different configurations. We looked at the in-service standard cross-section. We looked at the same as the first one, except a 10-foot high suicide barrier was mounted on the top in case that was needed by the owner in the future. And we also looked at the construction stage, which consisted of the standard cross-section with no barriers. Now, this sectional model was subjected to various angles of attack, and they actually tested it up to 175 miles per hour in the wind tunnel and no flutter instability in smooth flow. So it performed very well. And as you can see, the design wind speed was 121 miles per hour and 101 for construction. So it definitely performed well and exceeded the design criteria by quite a bit. So here's what that sectional model looks like in the lab. So on the left is in smooth flow, and on the right is in turbulent flow. And the turbulent flow was replicated by use of that grid system that's shown in the background. The third component of phase 1 is wind buffeting. So they take the aerodynamic coefficients that they got from the sectional model, and then they check the buffeting using a piece of software called RM Bridge. 3 analysis stages were looked at: an in-service stage, a critical construction stage, otherwise known as the Christmas tree stage, and then a post-earthquake analysis. The analysis determined that buffeting forces were well within the structural capacity of the bridge. However, there was some excessive movement of the superstructure under buffeting wind, otherwise known as the seesaw effect. And we'll talk a little bit later about how that was mitigated for. So that was phase 1. Then we move into phase 2. Now, why do we need to go to phase 2? Sectional model performs so well in the wind tunnel. Well, you need to do full-scale experiments as a double check. Computer programs aren't advanced enough to do the computational analysis. So you got to do a second round of tests on a full aeroelastic model. And in this case, a model was built to 1:80 scale. This model consisted of the main span bridge as well as the approach spans between hinges. So the total bridge length was 4,100 feet. And at 1:80 scale, that translates to about just a little over 50-foot model in the wind tunnel. It was tested under both smooth and turbulent flow. We looked at 3 conditions. We looked at the in-service full model and 2 construction stages. We looked at max cantilever and a freestanding tower. The stability of the entire bridge length is tested to ensure that there are no surprises. The aeroelastic model covered 3 areas of design. We looked at the overall stability in high winds. We looked at pedestrian comfort just in normal everyday winds. And then you also check buffeting under relatively high winds just to make sure that there's enough strength designed into the bridge to carry the wind loads. And then once the testing is performed, you can complete your design and confirm loads and the load combinations. So here's what those models look like on paper. Up top is that full in-service model. And then in the middle, we have that the construction stage, maximum cantilever. And then down below, we have the freestanding tower. So what do these look like in the wind tunnel? Here's up top, here's that full model in turbulent flow. And you can actually see they replicated the terrain and the existing buildings that were on at the construction site. And then down below is the model in smooth flow without the terrain model. Top view here shows that max cantilever model and then the freestanding tower. So what were the results? Well, the testing confirmed satisfactory aeroelastic performance of the completed bridge in both smooth and turbulent flow. As far as the construction stage models, there was no adverse aeroelastic vibrations for the max balance cantilever configuration. However, the freestanding tower did exhibit some vortex shedding and galloping type excitations under smooth flow. However, that went away under turbulent flow. So we're kind of in a little bit of a gray area, but out of an abundance of caution, the contractor decided to install temporary tune mass dampers at the tops of the towers to prevent that possible galloping response of the freestanding tower. Also, temporary stability towers were constructed to prevent weather veining around the axis of the tower. And also, you remember back in phase 1 under the buffeting analysis, there was the seesaw effect that was mitigated for by introducing this temporary stability tower. And then finally, internal dampers were installed at the ends of the stay cables to suppress vibrations in the cables from wind. So that's the end of phase 2. And then we have phase 3, which is the stay cable rain wind induced vibration and pedestrian comfort study report. We investigated 2 key vibration serviceability requirements. We want to ensure that the superstructure vibrations don't induce pedestrian discomfort, and you want to ensure that excessive vibrations of the stay cables do not occur. There's nothing really surprising that came out of this report. Helical fillets were installed on the stay cables. This is typical to reduce or eliminate the effects of rain, wind, and vortex-induced vibrations. Also provided some additional damping by introducing some friction dampers into the stay cables. So this next slide on the left, we show some of the specifications for the tune mass dampers. And on the bottom right, there's just a partial shot of what the tune mass damper looked like. It was a pretty enclosed space, so it was hard to get a good picture of that. Next slide, we see the temporary stability towers. There it is there with the cross bracing. And then in the bottom right, we could see a photo of what those internal stay cable dampers look like. So that's wind. So now let's move on to seismic. Southern California is an earthquake country. Fortunately, no active faults across the bridge. However, as represented by the bullseye here, the bridge is located between 2 active faults. On the left, we have the Palos Verdes fault, which is about 3.1 miles to the west. And then to the east, we have the Newport, Inglewood, Rose Canyon fault. This is the fault that triggered the infamous 1930 earthquake in the city of Long Beach, which caused a lot of destruction. Largest earthquake expected to occur in Long Beach in 1,000 years is 6.5 to 7.5 on the moment magnitude scale. Back in July of 2019, there was a 7.1 magnitude Ridgecrest earthquake, which struck approximately 150 miles northeast of the bridge as the crow flies. We did have some workers that were on the structure at the time, and they felt the movement. They were evacuated from the bridge as a precautionary measure, and then the bridge was inspected, and we didn't find any adverse effects from the earthquake, so the bridge definitely performed as designed during that event. So what's the design strategy for seismic? Well, you want to have a superstructure with points of isolation, which means the approach bridges are seismically isolated from the main span bridge. Looking at 2 earthquake events, a lower level functional evaluation earthquake, otherwise known as FEE, and a higher level safety evaluation earthquake, otherwise known as SEE. And the seismic demands are determined based on a nonlinear time history analysis using a piece of software called LS-DYNA. And here's the definition of FEE as a 60% probability of occurrence in 100 years, peak ground acceleration of 0.22 g. You can see the acceleration response spectrum curves above, and then down below, the same for the SEE, which has a 10% probability of exceedance in 100 years, peak ground acceleration of 0.62 g. The piles for the bridge are designed for the exact soil conditions at their particular location. There are liquefiable soils, so the depth of the piles were extended beyond the liquefaction zone. The approach columns and towers also contain ductile zones or plastic hinges near the base. The tower also, the main span towers also have a plastic hinge at deck level. Now, for the expansion joints at the ends of the bridge, look at these these are the translations under that SEE earthquake. You can see these are pretty significant. Transverse 70 inches, longitudinal -62 plus 59. So what the design builder did, he really did a global search to try and find a joint that would accommodate these extreme movements. There was a joint built by a company in Germany, which was a modular swivel joint with an integrated fuse box. So we used that technology from Germany, but in order to satisfy the Buy America requirements, the joint was fabricated in the US. And this was the first use of this type of joint in the state of California. So here's a shot of what that joint looks like in the fab shop. And you can see the fuse boxes over here on the right, or excuse me, on the left-hand side. And there's the joint being lowered in place out on the bridge site. Here's a shot of them installing the rails on the joint. And there's the completed assembly on the left, and on the right is a shot underneath the joint looking up. So that was a substructure seismic. So for the superstructure, cable-stayed bridges are ideally suited to resist earthquake demands. Remember back when we talked about wind, they're very flexible. It's really built into their DNA. The main span bridge is going to have a controlled sway during an earthquake. Uplift is going to be prevented at the ends of the bridge by tie downs, and the bearings have been detailed to avoid disassembly under small uplifts. Now, in order to control the relative movement between the superstructure and substructure and to dissipate the seismic energy, dampers are needed. And you can see the word here, passive dampers. So what we mean by that is Caltrans has had a lot of trouble across the state with leaking dampers. So this was a challenge for the design builder. And the solution that they came up with was to design a damper with a fuse. What this means is that during in-service loading, ambient loads such as temperature, live loading, wind, the damper would not be active. So it would essentially behave as a rigid link, transferring force into the tower. But however, once the force, the calculated strength limit state force was exceeded, that fuse would break, and then the dampers would become active and start to dissipate energy. So there's 6 of these dampers in the longitudinal direction at each tower, 3 in the transverse direction, and then the end bends. The end bends have 2 longitudinal dampers and 2 transverse. This is going to be one of the most wired bridges in the country. There are 77 accelerometers installed to monitor and record the bridge response during an earthquake. The data is going to be sent to the California Strong Motion Instrumentation Program. So engineers and geologists from around the world can analyze the bridge's performance and help improve earthquake resistance for future bridges, buildings, and other structures. So this next slide just lists the different components of the seismic dampers. Here's a shot of the damper being tested. All the dampers were tested down at UC San Diego. Here's a view on the left showing the transverse dampers getting ready to be installed. On the right, they're being attached to the transverse damper bracket. And you can see the dampers in the transverse direction are below deck level. And in the longitudinal direction, they are above deck level. And you can see there's 2 planes, 3 dampers in each plane to get you those 6 longitudinal dampers. And here's an elevation view, and you can just kind of get a sense for the size of these elements. So that's seismic criteria. So now let's transition to the last criteria we're going to talk about, and that's ATVA. So the RFP has a blast load analysis that were incorporated as part of the security requirements. We evaluated the structural vulnerability of the towers at the base, at deck level, in the stay cable system, and the deck system. And these key structural elements were modified to increase their resistance to potential terrorist attacks or accidents. So today I'm going to talk to you about the design that was done for the tower at deck level and then the stay cable system. So for the tower at deck level, both the design builder and the owner had an analysis model that they developed, but they were getting conflicting results. So in order to break the tie, so to speak, WSP contracted with the Army Corps of Engineers to have them build an analysis model as well to try and compare the results. And when we were talking to the Army Corps about this, they noticed that we were using a spherical charge in our analysis. However, they were saying that a prismatic charge more accurately reflected a real world blast. And their software was able to accommodate this type of analysis. So when they ran their analysis, they were finding that the thickness of the plate was such that there was a breach being caused when the blast was when they analyzed for the blast. So what they did is they increased the thickness of the steel plate. And you'll remember back when we were talking about the steel design criteria that grade 50 high performance steel was used everywhere except for the ATVA plate. So that's what they did. They also, not only did they bump up the thickness, but they increased the grade of steel from 50 to 100. When they did that, it showed that the tower armoring around the tower deck level performed as designed. However, Federal Highway Administration wanted to validate those results. So they asked the Army Corps to build a physical model of the tower. And that's what they did. And that's shown here, that a 3/8 scale model of the tower was built. This is what it looks like before the blast. I mentioned that armoring, the steel plate that was installed around the perimeter of the tower. The charge was placed right here, and over here on the right-hand side, this was where all the instrumentation and recording devices were set. So after this was all ready to go, test was conducted at Fort Polk in Louisiana. This was back in October of 2015. Several of us were there from the project, walked back about a quarter mile to witness the blast. And here I have a short video of that blast. So you can see I was recording this on my phone, and I didn't drop my phone. That was me ducking from the blast wave. It was sort of a natural reaction. So I wasn't expecting to see the blast or to feel the blast. So after feeling the blast wave and feeling the power of the blast, I was expecting as we were walking down that the tower would be blown to smithereens. However, when we got there, the tower performed as expected according to the model. And this is what it looked like. Very minor damage. Some of the bolts were sheared off right where the charge was placed, and there was some spalling of concrete. And then inside the tower, there was also some concrete spalling, but overall, it performed as expected and actually passed with flying colors. So that was a tower at deck level. I mentioned the other system I wanted to talk, or test that was done, was for the stay cables. So there was a proprietary armoring system that's installed at the bottom of the stay cables near deck level. That system is shown here. We tested both a 43 strand and a 109 strand bundle. This is the 109 strand bundle. The charge was placed right around the center of the stay cable. So this is what the blast, or what the stay cable looked like before the blast. And this is what it looked like afterwards. So after this occurred, engineers started to go up and segregate the wires into broken and unbroken. And the acceptance criteria was that there had to be less than 25% broken wires. And it turns out that I think there was a total of approximately 6 tests that were conducted on these stay cable systems. And it turned out that I think the most broken wires was 19%. So all of them passed and there were no issues. Everything performed as expected. So that's the design criteria I wanted to talk to you about today. So now let's transition to construction. So we're going to start with the towers and then go over to the superstructure. So for the main span towers, we're going to start from the bottom, work our way up. So here's just a schematic showing the cast and drilled hole piles that were installed. There were 12 8-foot diameter piles that support each of the tower foundations. So if I start here over in step A, the first step for installing these piles is to twist a large temporary casing into the ground with an oscillator. After that, soil is removed from inside the casing and then the rebar cage is lowered into place. Once that is done, then concrete is poured and the temporary steel casing is extracted. And then the final step involves the pile tip grouting. You'll remember early on in the presentation, I talked about one of the first. This was the first use of pile tip grouting in the state of California. This allowed the designer to use some of the base resistance of the piles, which ended up reducing the length of some of the piles that were constructed. In some instances, they were able to reduce the length by up to 30%. So this was ended up being a significant cost savings. Also, there were a total of 352 piles on the project. Each of those were non-destructively tested using gamma-gamma logging. And the results of those tests were that there were only, out of those 352 piles, only 2 anomalies. And those anomalies were mitigated by using a structural bridge. So here's what those steps look like in real life. So on the left, you can see that temporary casing, the clamshell bucket going down to excavate the soil. Here's a shot of Tower 17 from above. You can see the 12 cast and drill hole piles, and you can see the octagonal shape of the tower at the base, which transitions to a diamond near the top. Here's beginning construction or installation of the reinforcing for the tower foundations. Here's the completed tower reinforcing. Mentioned the elements greater than 7 feet in thickness required cooling tubes, and the tower foundations definitely qualified. Out widths were almost 90 feet, so you can see the large number of cooling tubes that were needed for this pour. And here's an aerial shot of Tower 17 being poured, approximately 3,300 cubic yards of concrete. This was a 14-hour continuous pour using, you can see the 3 concrete pump trucks. So that's the foundation, and then we start to work our way vertical. Here's Tower 17. This is right around deck level, so around 200 feet. We're getting ready to install the interior shear plates in this view. Near the top of the tower are the steel anchor boxes for the stay cables. Here's what they look like sitting on the ground. You can see the shear studs, which will allow the anchor box to be composite with the concrete tower. And here's that same anchor box with all the reinforcing steel installed. So you can see how the significant amount of steel that was involved in the construction of these towers. So here's Tower 16. You can see the Doka forms up top. And then here is the tower top with that diamond-shaped cross-section at the top at 515 feet. These are now the tallest structures in the city of Long Beach. So that's the tower. So now let's move on to the star of the show, the main span superstructure. So I'm going to walk you through the construction sequence for the main span. So up top here, so once the towers are constructed and the end bents, the next step is to erect a temporary falsework around each tower. Once that temporary falsework is erected, they start building a 100-foot section of the superstructure on the ground. Once that section is completed, it will be lifted and placed on top of the temporary falsework. And then they start to install the first sets of stay cables. Once those first sets of stay cables are installed, the derrick crane is placed on top of the pier table, that first 100-foot long segment, and then the temporary falsework is removed, and you can start to begin your balanced cantilever construction, building out from each side of the tower until you land on the end bent, and then you finish up with the main span closure. So those segments, that balanced cantilever construction, these are 50-foot segments, and these are the steps that are involved. And each of these steps, as you can see, have a type of surveying that's performed after each one. So the first step is to install the structural steel. This consists of the edge girders, the floor beams, and the stringers. Then you want to install the stay cables, then install the precast deck panels, pour the stitches, and then restress the cables. So those were the 5 typical steps, and the cycle time was approximately 45 to 50 days to complete. Now here's what that looks like out in the field. So the right-hand side, the edge girder has already been bolted up. Left-hand side is being lowered into position, getting ready to be bolted to the edge girder previous to it. Each segment contains 3 floor beams. So we got the first floor beam in place, and then they're raising up the second floor beam to connect to the edge girders. Here's a view from the underside with all 3 edge girders installed, as well as the stringers. So it's now ready for the stay cables and the deck panels. So here we have one of the stay cables being installed. Here's a shot out at the casting yard. Here's one of the deck panels before the concrete is poured. So there's that stainless steel reinforcing I mentioned earlier in the presentation. Here's the ducts for the longitudinal post-tensioning. And here's what a completed deck panel looks like at the casting yard. That panel is then brought out into the field, lowered into place by the derrick crane. And here's an aerial shot that shows the stitch pours being made. These will allow the deck panels to be composite with the structural floor system underneath. Here's a view of the towers and some of the stay cables. Here's main span segment 6. This is shown at tower 17. There are a total of 9 segments. So we're getting near the end here, and here's segment 9 under construction. And here's the main span closure segment. So here they're starting to install the last edge girder. This next slide shows the final floor beam being put in place. And I mentioned the main span bike path, so you can see the cantilever brackets right here for that bike path. They're lowering the panel into place, and then in the bottom right, we see the completed bike path with the railing. And then finally, the completed structure. This shot was taken October 2nd of 2020 for the virtual opening. I'm originally from the East Coast, so a big Eagles fan. And I always got excited during Sunday night, Monday night football games when they would show shots of the Ben Franklin Bridge lit up. So I'm excited and anxious to see this structure at night when the Chargers and the Rams are playing at SoFi Stadium. So I think it will look really cool. So now let's go into lessons learned. So my title slide here is my first lesson. So the previous day, one of the inspectors was driving around the job site, came back the next day, wasn't paying attention. The contractor had excavated a hole. So that's the first lesson, is to always be aware of your surroundings. Fortunately, no one was hurt here. So, but this is an important lesson. Always be cognizant of what's going on out on the job site. Here's a list of some of the lessons learned. First is to require a review of the RFP and proposals by the firm administering the contract. This will ensure that there are no conflicts and eliminate any errors in the documents. Pre-qualify the DB contractors. The design build contract needs to be awarded based on best value, not price. All reviewers and administrators must be familiar with design bid build versus design build. This will ensure efficiency in the review. In order to do that, it's recommended that workshops or training for all staff be conducted on roles and responsibilities. Want to ensure your contract includes enforcement measures and damages specified to address any deficiencies in the execution of the contract. Want to ensure that all third-party and utility agreements are included in the RFP. Acquire all right-of-way and clear utilities before issuing notice of proceed. There's a lot of news articles on these mega projects where there's holdup and delays because all of the right-of-way has not been required. So this is important. You want to conduct regular critical issue meetings with the key stakeholders. We started doing this about halfway through the project, and it turned out to be very beneficial. We were able to address issues in a timely fashion and arrive at a path forward in collaboration with all of the other stakeholders. It was definitely a time saver. Your quality program must be well defined. And if the owner wants or does not want something, it has to be clearly stated in the RFP. Celebrate successes, milestones with all stakeholders often. Measure twice, cut once. We had some issues on the main span superstructure erection where there was some survey busts and there was also some fit up issues for the survey bust. It caused us to unnecessarily de-stress some of the stake cables, which led to some delays. So it's very important to do that and communicate. Can't emphasize it more. There's especially on projects as large as this with a lot of stakeholders, a lot of moving parts, communication becomes extremely important. And then finally, remain open-minded to innovation and most of all, have fun. So that concludes my presentation. I want to thank you all for listening to my session, and a reminder that next year's convention will be held in Chicago. And with that, I will be more than happy to answer any questions you may have. Thanks again.